Good morning. So we are in the middle, or more than in the middle of module 2. Note that the models are organized according to the subject, and not according to the session. So we are in the third session, but still on the second module. Okay, let me remind you briefly, recall what we did yesterday. So the main concept. So we were describing abstract argumentation frameworks, which are just directed graphs in which the nodes are arguments and the arrows directed arrows just represent attacks among arguments. In order to give semantics to this directed graph, we use two types of semantics. One is defined by extension, and the other one is defined by three-value labeling. We saw that these two kinds of views are equivalent, and if we use and both of them help us to determine what argument should be accepted. Okay, so for instance, if we adopt the extension-based semantics, we have two main considerations. Okay, so each extension is an option, a set of arguments that we may accept, and how we determine those sets. Well, we have two main considerations. One of them is consistent, so there shouldn't be any attack between arguments at the same set, the same extension, so they can stand together. The other criterion is admissibility. Okay, so any extension must defend all of its arguments, so they can stand on their own. In order to define complete extension, we added a third criterion, which says that not only that the extension is conflict-free and admissible, but also complete extension should defend only those arguments outside. Okay, so these are the options. The complete extensions are the options of how to among those options. Well, according to Duke's semantics, we have several smallest extensions, or we can take the preferred extension, the preferred complete extension, which are the stable extension, those that attack all the other arguments and all the arguments outside this extension, or semi-stable. So we have several options how to choose among the complete extensions. One, we do that. So we have a extension framework, and we have a specific semantics. Then we can define an entailment relation. And there are two kinds of entailment relations: the skeptical entailment, according to which conclusion must be part of all the extensions that we choose according to our semantics. And according to the credulous entailment, should I use the microphone or is it okay? And according to the credulous entailment, something follows from the argumentation framework. Imagine it will be in one of the extensions. Then we need to correspond from the extension. Okay, and then this is abstract argumentation framework because the arguments are totally abstract entities. Once we switch to logical argumentation framework, we want that each argument will follow from an underlying logic. Okay, so we choose our favorite logic. According to this logic, we produce arguments, and so and then we set up an argumentation framework. So according to logical argumentation framework, arguments are just sequence. Okay, these expressions. Okay, so we have a finite set of assumptions denoted by gamma, and a conclusion denoted by psi, and the only requirement that we enforce on those sequence is that the conclusion should logically follow from the assumption. Okay? Nothing else. Of course, it's supposed to be a subset of our knowledge base. But basically, the only thing that we want is that the conclusion will follow from the assumption. Of course, we would like to have a constructible way of producing those sequences, and we do this by sequence calculus. Okay, so these are the arguments. How we produce attacks. So attacks are produced now by new attack rules. So sequence calculi have inference rules, and the idea is to extend the sequence calculi by new types of rules which describe attacks. Okay, and this is more or less where we stopped yesterday. Okay, so let's continue with the attack. Okay, so we may incorporate different kinds of attacks in our system. Yesterday I described one kind of attack, which I called undercut. Okay, so the argument in green denotes the attacker. Those in red are the attack arguments, and in the middle we have the conditions for the attack. Okay, so according to undercut, the attacker attacks the attack argument in case that the conclusion of the attacker is logically equivalent. If they are equivalent, because we have two corresponding sequence here, the conclusion of the attacker is logically equivalent to some subset of the support of the attack argument. In this case, we say that the attack argument is attack, which means intuitively that we cannot adopt both arguments together because there are some conflicts. Okay? There are many attack rules that we can define. For instance, a variation of undercut is direct undercut. So you see here in direct undercut that the conclusion of the attacker is equivalent to the negation of a specific assumption in the attack. So therefore, we call it direct. Attack a specific form. Yes. I was wondering why the undercut is equivalent Okay, for this we have another way. Okay, so in the fifth, the fifth is has a weaker condition. So you can just choose your favorite attack. Okay? Yeah. No. You must have something to attack in the so we have some side conditions in this what the side condition here is that, of course, the attack support, the subset of support that is attacked should not be right. Okay, so this is undercut, direct undercut. The fit, as I said, is a variation, a weaker variation of undercut, and also we can define accordingly direct defeat. We see that instead of equivalent, we just require that the conclusion will entail the negation of one of the supports of the attack argument. Okay, and then we have other arguments. For instance, we can refer to the conclusions of both attacking and attack arguments. So, for instance, in this case, we see that the conclusion of the attacking argument is equivalent to the negation of the conclusion of the attack argument. So this rule reverses. Defeating rebuttal is like the difference between undercut and defeat. So instead of equivalence, we just require one direction. Conclusion entails the negation of and the negation of the conclusion of the attack. Another useful attack that we might want to use is what is called consistency undercut. And the intuitive explanation here is that if we want to exclude the attack argument in this case because it contains some contradictions. Okay? So that here we have a tautological argument which attacks some support of the attack argument because it is contradictory to the negation of what I told you. So this is another useful attack. Of course, there are relations between those attack rules. For instance, direct attack in a specific, direct undercut in a specific case of undercut. So the attack rules are some of them are related. Okay, let me show you now some instantiations of this logical argumentation framework. How we organize, what we do with those arguments, and that. So the one that I have started to describe is called sequent-based argumentation. This will be the primary approach in this course, in which we have sequence and attacks among the sequence, and now we can just use, as we did with our abstract argumentation framework, which we can use the same framework, the same graphs, but now the nodes are sequence. Okay, so this is the same definition as abstract argumentation framework, except that you see the nodes are the arguments that are induced by the subset of assumption. Okay, gamma implies phi, where gamma is a subset of F. So this is our knowledge base. And attacks are just attack rules that we choose to use in our framework. Here's an example. So suppose that we have this set, okay, P, not P, and Q. These are our assumptions. So now we produce a sequence out of this set. So we, for instance, like P, we can produce not P implies not P, we can produce the tautological sequence, etc., etc. And then we have an argumentation framework. Once we have this argumentation framework, we can impose on it some semantics. Okay, so for instance, we can use the notion of attack as before. Okay, so now this sequence attacks that one. We can use the notion of defense. So this sequence defends that sequence. Let me say a few words about why it defends that sequence. So what is happening? Okay. So we have this set S. What if we want to be able to derive Q here, and we don't want to be able to derive not from this set? Now, how can we, by sequence, how can we produce sequence that, according to whose conclusion is not, so suppose that we have an person, okay, that wants to produce somehow the conclusion of not consistent. How can it be done? For that, we have two options. Both of them are based on contradictions. One option is to say we need, suppose of course, one option is to take P not P and to the right not Q. See here. Okay? The other option is similar, just take P not Q. So that makes us that, and then we still can derive not Q. However, so these are the two options. But once we use consistency undercut, for instance, we can attack those ways of consistency. Why? Because we have, and we can see, we can reduce P or not P. And this ontological argument attacks this one. Because also according to other stuff, because this is similar to the negation of the conjunction of this. And similarly, we have that. So this is what we see here. Okay? This tautological sequence attacks any attempt to produce sequence whose conclusions are not Q. And therefore, we actually we see that this tautological sequence defends Q. This is the reason that we can, in fact, conclude Q here. Q, and we cannot include the point. That's the point. Yes. Now, well, in this example, I think that I'm using the undercut. It depends on the example. Yes, of course. You choose a specific attack rule or set of attack rules, and then you compute your argumentation. So this argumentation fragment is a fragment of the biggest one, which is induced by itself together with. Okay, let me continue so we can use the other notions of two. Yeah.
Being just be attacks and it's attacked by no P. There's no P. I can't be in the same set. But they both can be together or not.
Right. I will show it in a minute. So again, we have the notion of defense, as I just showed you. We have the notion of conflict freeness. We have the notion of admissibility. Okay, I said that defense itself. We have the notion of complete extension. So you see here, this is one of the here you see that a complete extension in which we have things like P together with the ontological sequence. We have another. We have preferred extension. This is one of the preferred extensions. But we have another preferred extension in which instead of things like P, we take not things like not P. These are the two preferred extensions in this case. In this case, these are also the stable extensions. So they are stable because each one of them attacks all the arguments outside the extension. And we have a grounded extension, which is this one, which is smallest. In which both P and not P are excluded. So we exclude all the complications. Okay, here is another example, a little bit more complicated. So we have S, we have the rules, many sequence, and then we can, as usual, compute the preferred stable extension, and this is computable, as I showed yesterday, by many techniques. That over PDF over. Here's another example. Since we allow any language, any compositional language, you can incorporate modality for it. Okay, so we can use, for instance, or with some knowledge base, like S, not this is the S. Direct undercut, and again we have this done for stable text. Last example for the moment is taken from beyond logic. So Marcelo mentioned this morning beyond logic, which is actually a model logic that deals with norms. So instead of necessity and probability, we talk about obligations and permissions. And this is one of the puzzles posed by John Hodges in the context of theoretic logic. So the puzzle says the following: if we have if a meal is served, one should not eat with fingers, while if the meal is asparagus, one is allowed to eat. One should eat. So this can be represented, for instance, as follows. So we can use the logic SPL. Some of the logic is actually the normal model logic KD, where O, the modality O, represents obligation, O, the law described this morning. And well, now the set of assumptions, the S is just that we have a meal, we have asparagus, and we have two entailment is the meal we should not to use the finger, but while we have a meat with asparagus, we ought to use this finger. What should be the attack rule here? Well, in this case, there are a lot of degree of freedom for defining attack rules. Note that in this case, this is a pragmatic case of specificity. A more specific obligation cancels or override a less specific. So in this case, we would like to say that since this formula is more specific than that one, because this formula assumes that we have a mean and also asparagus is served, then this formula should override that one. Okay, and we can define specific undercut that exactly expresses it. Okay, we have the usual undercut together with some more assumptions that are related to more or less specificity. So this rule will actually pose an attack of this formula over that. Okay, now we can define entailment, well, because this is our main purpose. So we're to be able to infer. So remember that when we talked about ASPIC argumentation framework, we had two kinds of entailment: skeptical one and credible. When we talk about logical argumentation framework, we actually have three kinds of entailment, because the skeptical entailment can split two kinds of skeptical entailment: the weaker one and the stronger one. So let me give you the definition. Okay, so we have a given fixed ASPIC argumentation framework. So we have already decided about the logic, about the attack rules, and also we have decided about what would be our semantics. So logic for producing the argument, attack for describing attack, among conflicting arguments, and semantics for selected what conflict extension work is like keys. According to this setting, we can define now different entailment relations. The first one, which is called strongly skeptical entailment, says that psi follows from S. Remember that S is the set of our background knowledge. Okay, so we can conclude psi from S if there is an argument in the intersection of all the extensions that we chose according to our semantics. So there is an argument in the intersections whose conclusions is phi. If there is such an argument in the intersection, then we can conclude psi. A weaker version of a weaker skeptical version is the following. Psi weakly skeptically follows from S if for every extension in our semantics, there is an argument whose conclusion is psi. So note the difference why this is strong and this is weak. According to the strong entailment, we require that the same argument should be in all the extensions. According to the weak entailment, we don't insist on the same argument. But so each extension may have a different argument, but with the same conclusion. So the supports may be different, but the conclusion should be the same. I will give you an example very soon. And the third one is the credulous semantics, which is similar to the one with abstract argumentation framework. And this it says that psi follow from F if there is some argument or some sequent in some extension whose conclusion is psi. Okay, let's come back to our running example, the simplest one. So remember that if we take this example, so it's classical logic with the set of P, not P and Q. And if we take, for instance, the grounded extension, so these two sequences are in the grounded extensions. So we can see, note that since we have only one extensor, remember that grounded extension, we can have only one grounded extension, unlike preferred and stable extension, for instance. Since we only have one extension, all the three versions of the entailments are actually the same, okay? Because intersection and union are the same once we use one extension, okay? So in this case, according to all the variations of the entailment, we can conclude from this set, once we use classical logic with undercut and the grounded semantics, we can infer, for instance, the tautologies, of course, and we can infer Q. Okay, while we cannot infer the other assumptions. So we cannot infer P and we cannot infer not P in the grounded extension. Okay, because they are excluded. See, they are outside the extension. And of course, we cannot infer not Q, which is obvious because what I've shown you earlier. Okay, in the example about asparagus, we have a similar result. So we have this set of assumptions, and since if we have specificity undercut, since this attacks that formula, then we can conclude that we ought to eat with fingers, while we cannot conclude the opposite. And this holds for every entailment relation with respect to all the semantics. This is the intuitive conclusion in this case. Okay, let's, as I hinted before, let's
see the relations among these entailments. So stronger credulous, strong skeptical entailment obviously implies weak skeptical entailment. Okay, remember the definition. Here we require that the same argument will be in the intersection, so it's obviously meet the weaker requirement. And this, of course, implies a credulous entailment, but the converse is not true. Let's see why. Here's an example. Consider this set, P and Q, not P and Q. Again, with classical logic and direct undercut. We will see, believe me now for now, that the preferred extensions and the stable extensions in this case are, we have two kinds of extensions. Both if we use preferred semantics or if you use stable semantics. One extension is consists of all the arguments that whose support is P and Q. So for instance, P and Q implies P, P and Q implies Q, etc., etc. And the other extension consists of all the sequence or the arguments whose support is based on this formula, not P and Q. So in this case, for instance, according to credulous semantics, we can infer P. Why? Because P is a conclusion of a sequence that belongs to this extension, right? However, we cannot imply P, we cannot infer P according to weak skeptical semantics. Why? Because there is no sequence whose conclusion is P in this extension. Okay, so we have two extensions, but only in this extension we have sequence whose conclusion is P. Therefore, we cannot infer P according to the weakly skeptical semantics. Moreover, weak skeptical semantics is weaker than strong skeptical semantics. We can see it here again. For instance, according to weak skeptical semantics, we can infer Q here. Why? Because there are sequence in both extensions whose conclusion is Q. Here we have P and Q implies Q. And here we have not P and Q implies Q. So we have in both extensions sequence whose conclusion is Q. However, according to the stronger skeptical entailment, we cannot infer Q. Why? Because we don't have the same sequence in both extensions. Here, a sequence whose conclusion is Q are based on this assumption, and here they are based on other assumptions. So we don't have a single argument that is an element of both extensions. Therefore, according to the weak skeptical semantics, we can infer Q, but we cannot infer Q according to the strong skeptical entailment. And later on, I will consider other interesting properties of those entailments, especially how those properties are affected by the choice of the logic and the attack rules. Of course, different logic may impose different entailments, and etc., etc. So I will consider this in more details later on. Okay, let me briefly conclude this model by a few notes about two other well-known approaches to logical argumentation, and then I will come back to sequence-based argumentation. One approach is ASPIC. I will just give an intuitive presentation of this system. So the basic principles are, this is again a deductive system. with some extensions that we will do similar things with sequence-based argumentation. Therefore, I will not tell you too much about how these extensions are enhancement are implemented in the ASPIC-based system. One generalization is that the background knowledge, the assumptions is split into two kinds of assumptions: strict assumptions and defeasible assumptions. So strict assumptions are assumptions that cannot be challenged. We take them for granted. And the defeasible assumptions are those who can be challenged. And also we have strict and defeasible rules. So the strict rules are deductively valid, while we have another kind of rules which we call defeasible rules, which are weaker. They're persuasive rules. I will give you an example in a minute. Again, we have this form of arguments, but the difference is that now arguments are no longer sequence, but the gamma is actually a tree structure for deriving the conclusion. And we have argumentation framework and use Dunk's style semantics. Let me give you just an illustration of how what is going on with ASPIC-like systems. So we have here three arguments. Okay, you see that the structure of argument is more it's more complicated than just sequence, because we have here a tree and a conclusion. Okay, this is the gamma, and we have a conclusion. Similar here, we have a tree-like structure whose root is the conclusion of the argument. So let's take an example. Suppose that we saw John in Holland Park. Okay. Now from this we infer that John was in Holland Park since we saw it. Note that this is a defeasible rule. It's not a logical conclusion because it is based on our senses. Okay? It's not a logical conclusion. Therefore, I denote it by a dashed line. Okay, so we conclude here that John was in Holland Park. Also, we know that Holland Park is in London. Therefore, we can infer, but this inference is a logical inference. If John was in Holland Park and Holland Park is in London, then John was in London. This is a logical inference in our logic. Okay, therefore it is denoted by straight lines. This is one argument. Another argument could be the following. David says that he saw John in Amsterdam. Again, by the feasible rule, we conclude that John was in Amsterdam. Now we have conflicts. One argument says that John was in Amsterdam. The other argument says that John was in London. So we have attack between them. Here's a third argument, okay? Now, John is a suspect in a robbery in Holland Park. Okay? David and John are friends. We know that. Okay? Therefore, we conclude, again, this is not a logical conclusion, but a defeasible conclusion. We conclude that David has reason to lie. He has reason to lie because he's a friend of John. Now, note that this conclusion attacks the inference that we made here. Since David has reason to lie, we may not infer from the fact that David says that he saw John in Amsterdam, we may not infer that John was in Amsterdam. So this attack is not on the facts or on the conclusion, but the attack is on the defeasible inference. Okay? So this is what happens in ASPIC systems. Let me give you another example. Okay, so we have, I will not get into details, but again, we have strict premises, defeasible premises, strict rules, defeasible rules. Now we can, just a minute, okay? Yes. Now we can construct arguments and attacks among arguments. And this forms a argumentation framework. Okay, so we can apply on it Dung semantics to conclude, for instance, these three arguments and exclude that argument. Okay? That's in principle ASPIC system without getting too much in details. Yes.
I didn't understand the fourth movement on some basic principles of ASPIC systems.
The fourth one?
1, 2, 3, 4. No, the fifth. I call it.
Fifth.
Attacks on the defeasible rules in the support.
Yeah, so we have attack may be on the defeasible rules in the support. So here you see that, for instance, this is a support of the conclusion, right? And we have here a defeasible rule, okay? And we have attack on defeasible rule. So attacks, so we have two different kinds of attack. This is attack between conclusion, and this is attack between one conclusion on the rule, the feasible rule.
Not only the data, but also the
Also the,
in
yes.
some cases.
Yes, but only the feasible one, not the logical one. You cannot attack logical rule, only the feasible. Okay, I also want to mention very quickly, because it's also well-known method in logical argumentation. There is also approach that is based on what is called assumption-based argumentation. Again, very, very quickly, what is the basic idea? So assumption-based argumentation system operate on sets of assumptions rather than individual arguments. So we have a set of formulae, and this may be viewed as a higher level of abstraction. So each set represents equivalence class on consistent, equivalence class that consists of arguments generated from the same assumption. So instead of considering specific argument, we consider sets and all the arguments that can be derived from those sets. Okay? So and then we have what is called assumption-based argumentation that consists again of a language, set of rules, defeasible assumption, and a negation operator. In fact, it is called a contrariness operator because it's not necessarily a logical negation. For instance, we can use contrary. You can use it in a broader sense. So for instance, the contrary of white is black, for instance, or the contrary of small, tall is small, etc., etc. So it need not be the logical negation. And we define attacks in a similar way. So we have inferences according to the gamma rules. And then we say that the set of assumption, the set S attacks psi, if we can derive something in which is contrary to phi. Right? So if there is a subset of set which and contrary to phi, which is derivable from that set. And then S attacks another set if there is a subset if S attacks some subset of the attacked set. Okay, and then we can. This is how usually our systems look like. So you see that we don't have argument, but we have sets in this case, and we can use the usual, you see, the usual Dung style definition, and we can produce accordingly entailment and consequences in a similar way, using the different kinds of semantics. The reason that I'm not talking in much detail about the other system is that there are translations, or at least partial translations with some restrictions among those methods, which can be, which are shown in those in paper, and moreover, there are relations between argumentation-based system to other method of having a non-monotonic reasoning. So some of you may know default logic, greater default logic, or epistemic logic. Adaptive logic, you discussed it last week, logic programming, and for all this logic, there are some translations between those formalism into, for instance, ABA system. Or at least there is a translation of some fragment of adaptive logic to ABA system, etc., etc. And I hope to discuss this in the 5th module, at least this relation between logic programming and argumentation-based systems. So argumentation-based, although it looks a little bit simple, it is rich enough to capture many other forms of non-monotonic. Okay, this completes the 2nd model. Let me now turn to the 3rd model. Okay, now that we are familiar more or less with different approaches to logical argumentation, let's consider some knowledge representation issue and rationality postulate. So this module consists of 2 main parts. In the first part, I will consider some knowledge representation consideration. It's very important in the concept of AI, the KRR, knowledge representation and reasoning. So I will go to this immediately. And in the second part, I will consider general properties, and I will show you some relations to reasoning with maximal consistency, some rationality postulates for evaluating the different entailment that I just described. But let me start with some knowledge representation consideration, and in particular, ways to extend the expressive power of our frame. How they can become more expressive. And there are several considerations here. I will talk about distinction between strict and defeasible premises, how these can be implemented in sequent-based calculus, in sequent-based argumentation. It is possible to extend arguments with priorities, to turn from sequence to hypersequence, to do some abductive reasoning, etc. So let me start with those extensions. First, how we can make a distinction between strict and defeasible premises. So in some cases, we want to divide our assumptions to 2 types. Assumptions that cannot be attacked, we call them the strict assumptions, and they are denoted by C. And the defeasible assumptions that can be attacked, which we denoted as before by S. How this can be implemented? Well, very simple. We just have to change our attack rule, to add side conditions to the attack rule that will prevent attacks on the strict assumptions. For instance, in undercut, if we are using undercut, we must say that the subset of the attacked argument should not contain any strict assumption. That the subset which we use for the attack. So if psi attacks some is equivalent to the negation of a subset of the attacked argument, then we can apply the undercut only if this subset does not contain strict assumption, because we want to exclude the strict assumptions from the attacked considerations. Okay, similarly, in direct undercut, we can directly attack some assumption in the support of the attacked argument, provided that this assumption does not belong to the strict assumptions. Okay, so we just have to add side conditions. Note that for consistency undercut, now we originally consistency for the attacker of consistency undercut were tautological sequence. Now we can use the left hand side of the attacker might not be empty. We can use gamma 1, provided that gamma 1 is consists of strict assumptions. So in this case, consistency undercuts means that we can attack an argument as long as their support contradicts some strict assumption. Okay, let's see how this is implemented. So here is the usual. I come back to one of the examples that I used before with S4 direct defeat and this set of assumptions. Those are now the defeasible assumptions. If you want to make P, so these are previously the assumptions. So we had P as a defeasible assumption. If you want to change the status of P to be a strict assumption and non-attackable assumption, then we can add this set C, which consists of P, and leave the other formulae as in the defeasible set. So now some attacks are excluded. For instance, previously A8 could attack A1. Why? Because you see the conclusion of A8 is not P, and therefore it can attack A1 whose support is P. But now, according to our revised definition, this attack is excluded. Why? Because P is not attackable anymore. Okay, so we get this set. And for instance, that argument becomes in the grounded semantics, becomes strictly valid. Okay, in fact, all the attacks of 8.8 are removed because A8, the conclusions of A8 is not P, which is the negation of the strict fact. Okay, let's now add priorities. I think that in the first session, someone asked me about whether we can define more substantial contradictions or whatever. And I replied that one way of doing this is by adding priority, which is very common in the context of argumentation framework. So the idea is to extend the logical formulae with numerical information, which may be attached to the defeasible assumption for reflecting preferences or confidence factors or whatever. Okay, so the idea is in this case, for instance, we can assign a priority to each formula. So you see now the priority of psi is some number in this case, and I will assume that lower values indicate higher priority. Of course, I may use not only natural number, but real number or whatever, but in this case, for simplicity, I will use natural numbers. Now, this extra information, this quantitative information can be used for making preferences among arguments. So this may be carried on according to different policies. So suppose that we now have a preference for each formula in our knowledge base, reflecting whatever, priority, confidence, or whatever you like. Now we have two arguments, okay, A1 and A2. And we want to make preferences between these arguments according to the numeric information that we have just added. How can we do it? Okay, we want to say that A1 is preferred to A2 according to our phi function, okay, the evaluation, the priority information. We may use different policies. For instance, we can compare the supports of each argument, gamma 1 versus gamma 2. Okay, and say that A1 is preferred to A2 if the most preferred support in gamma 1 is better than the most preferred support of gamma 2. This is a min-min comparison. Note that this comparison is not very appropriate if we allow left monotonicity, because then we can just artificially add prioritized assumptions to the support of the arguments. So we could use, we could use a refined criterion, which refers to the set difference between the support of this element argument. Or we can use a very popular criterion for comparing arguments, which is called the weakest link principle. We take the weakest argument, a weakest formula in the support of each argument, and we compare them. So if the weaker formula in the support of A1 is still better than the weakest support of the A2, then A1 is preferred to the A2. So we compare the weakest links of these in the support of the two arguments. Here is a more radical criterion according to which the least prioritized formula in the support of A1 is still better than the best support in A2. So this means that all the supports of A1 are better than the supports of A2. And we can use other criteria. For instance, we can use aggregation functions. So we can sum all the priorities in each of the supports of A1 and A2 and compare the sum. Another popular approach is according to a Brefka stratification criterion. And the idea is the following. So again, we want to compare the support of A1 and the support of A2. And the idea is to make certifications on each support. So we take, for instance, gamma 1, and we divide it to several strata, certification. So in each certification consists of all the formulas with the same priority. Okay, so we look at the support of A1 and all the formulas that have priority 1, they belong to the first certifications of gamma 1. All those who have priority 2 are in the second certification, and so forth and so on. And then we can compare the certifications of A1 and of the support of A1 and A2 as follows. We say that A1 is preferred over A2 if either A1 is a tautological sequence, so gamma 1 is empty, or the highest stratas of gamma 1 and gamma 2 are equivalent, and the next certification of A1 strictly contains the next certification of A2, of the support of A2. Okay? So in the I-1 highest level, they are the same, the certifications are the same, and in the next level, A1 becomes better than A2. Okay?
Question.
Yes.
Is there a comparison between the different criteria? Pros and cons?
Yeah. Well, we can. Well, some, for instance, one comparison is that some of them are partial order, and so the kind of order that they impose. Some of them implies the other, so we can compare. Of course, there are many ways to compare those methods
for some problems.
Yes, exactly.
That seems to be like a lexicographic order.
Here, yes, that's true. we can switch between subset relation to cardinality, okay? So we can still consider stratifications, but instead of relating them in terms of subset relation, we can just count the number of formulas in each strata and accordingly make the comparison. Okay, so how we can incorporate those priorities. So now we can again compute argumentation framework, but we should take into account the priorities. How this is done? Instead of attacks, we define the notion of defeat. So defeat now is attack, the attack relation, together with preference considerations. So we say that A1 defeats A2 if there is an attack rule according to which A1 attacks A2. So there is an application of, we can apply some attacks of A1 over A2, but this is not enough now. A2 should not be preferred over A1. Okay? For applying this attack, we must make sure that the attack argument is not preferred over the attacking argument. And once we do this, we immediately have prioritized argumentation framework as before. So we again can compute the arguments that are induced from a set of assumptions. These are the nodes. And instead of attacks, we have defeats that take into account not only the attacks, but also the preference consideration. And again, we can apply Dung semantics. So just to demonstrate this, so here we have again classical logic undercut with some set of assumptions. This is the standard argumentation framework. Now, what we can do is we can attach values or priorities to our assumptions. Okay, so suppose that P is assigned 1. This is the most preferred assumption. Then we have Q, which is assigned 2, and not P or not Q is assigned 3. Okay? And we want to apply the subset certification comparison. So note that now all the attacks that are marked by red arrow are not relevant, they are not applied anymore. Let's see why. For instance, without priorities, we see that A7, for instance, attack A1. Why? Because the conclusion of A7 is P and A1 is based on P. Okay? But since P is it has the highest priority, we cannot any longer allow this attack because A1 is preferred over A7. Okay? Even the first certification, you see, the first certification of A7 is empty because it is based on assumptions who the support of in A7 are assigned either 2 or 3, while the first certification of A1 is not empty, it consists of P. P is assigned 1. Therefore, although A7 attacks A1, it does not defeat A1. Okay? And therefore, we should exclude those red arrows and end up with a different argumentation framework that takes care of those attacks. Yes. Let me conclude this enhancement by priorities by considering some more complex example. So suppose that we have a flat owner that negotiates the construction of swimming pool, denoted by S, tennis court, denoted by T, and a private car park denoted by P. He negotiates this with his tenants. It is known that any investment in 2 or more of these facilities will increase the rent, denoted by R. Otherwise, the rent will not be changed. The tenant do not have a particular preference among these three options, but if they have to make a choice, they prefer not to have two support facilities. So they prefer not to have both S and T, the swimming pool and the tennis court. And they definitely do not want to increase the rent. Based on these inputs, that owner needs to reach a recommendation about the facility or the facilities to be constructed. How can we represent this in terms of an argumentation framework? Okay, so one thing that we know is that the rent should not be increased. That this is the highest preference of the tenants. So we have not R. The rent increases if more than two facilities are constructed. So we have another formula which says that the rent will be increased if either we have one of the two facilities, ST, SP, or TP. And as was written in the description, no two sport facilities should be constructed. So we have two other formulas: S implies not T, and T implies not S. Now we should represent it in terms of argumentation framework. Let's take classical logic, and our set of assumptions consists of all those assumptions. So we have the three facilities, we don't want to increase the rent, and the three formulas representing the preferences of the tenants. Now we should make preferences among these formulae. So the not R is of the highest preference because the tenant do not want to have the rent increased. Psi 1 till psi 3 we are of the second highest priority. So we assign them the value 2. And the other facilities are assigned just 3 because a priori we don't have any preference among them. And let's compare these. Let's use the subset classification approach. So here are some observations. I can of course show you the argumentation framework with all the computations, but let's wave hands a little bit, as Daniela says, and let me give you some considerations how this is resolved.
Sorry, in this case, if I'm not mistaken,
Yes.
side 2 and side 3, if you have classical logic, they are equivalent. So it doesn't make a difference. Even in the pessimistic one.
If we yes, that's true, but you can use them.
Both saying the same, so maybe you can
Yeah.
sort of resiliency.
Okay, yeah, that's true. Yeah, what they say. That's eventually each one says that we should not have both of them together. Okay, so here are some observations. First, the first observation is that we should not have two facilities. Why? Because any arguments for the two facilities, okay, if we have x, y, double arrow x and y for some x, y among these three facilities is defeated by this argument. So if we have not R together with psi 1, we conclude that we shouldn't have two facilities together. Moreover, no sport facility should be built because the arguments for each one of the sport facilities is undercut, defeated by these arguments. For instance, if we take T and psi 3, we conclude not S. And by modus ponens, okay, and if we take S and psi 2, or again, they are equivalent, so either we use modus tollens or modus ponens, we conclude not T. Okay, so no sport facility should be built, which leaves us with the third option, the parking lot. And the parking lot is supported. Why? Because this argument saying that we should conclude, we should construct parking lot, the conclusion is P, is defended. Why? Because any attack on the assumptions here is by arguments whose support is classically inconsistent. So in order to attack this argument, we need an argument whose support is classically inconsistent. And these attacks can be counter-attacked, so they can be defeated by a tautological argument which takes the negation of all the elementaries. So altogether, by introducing those preferences together with the argumentation framework considerations that I sketched here very quickly, we conclude in this case that only parking lot is built, but we need for this preferences. Okay, let me conclude. I concluding this session a little bit earlier because we have the webinar shortly. So let me just say that tomorrow we shall start with another extension of the for sequence-based argumentation. We will extend them by hypersequence, and I will justify and tell you why this is useful. We shall talk about abductive reasoning in case of sequence-based argumentation. Then we will go on to consistency considerations and then general properties showing why reasoning with argumentation framework is closely related to reasoning with maximal consistency, and we shall consider some rationality. So I will conclude here. Since we have a short time until the webinar, if you have any questions, either ask them tomorrow or feel free to ask me during the break, okay? Because we don't have any more time.